Hello everyone. Welcome to this lecture on topology. In the previous lectures, we have studied about topological spaces, basis for a topology, subspaces, product of two topological spaces, and continuous functions. Now, in this lecture, we'll study about separation axioms. Separation axiom plays a very important role in the study of topology. It studies about the separation of points or separation of closed sets by open sets. In this lecture, we will study about lower separation axioms. Lower separation axioms deals with T1 spaces, T2 spaces, and Eurytion spaces. T2 spaces are also known as Hausdorff spaces. So let us define what is a T1 space. Let X be a topological space with topology tau. Here we have the space X with topology tau. Then X is said to be a T1 space if for every pair of distinct points X and Y in X, there exist two open sets U and V such that U contains X but not Y and V contains Y but not X. So if this is our topological space X and for any 2 points X and Y, there exists an open set U which contains X but not Y. If we have a topological space X, for any two distinct points X and Y in X, there exist two open sets U and V where this U contains X but not Y and V contains Y but not X. If this condition satisfies for every pair of points X and Y, then we say that X is a T1 topological space. Let us see an example here. Let X be the set containing 3 points A, B, C. Let the topology defined on X be whole space X, empty set containing 2 points A, B, set containing 2 point B, C, and singleton set B. Clearly, this is a topology on X because it satisfies all the conditions of being a topology. Here, to show that whether this topological space X is a T1 space or not, we have to pick any 2 points and we have to show that it satisfies the condition of a T1 space or not. Let us consider 2 points, 2 distinct points B and C, and we have seen that there are 5 open sets in this topology, and out of those 5 open sets, this open set AB contains B, this open set singleton open set B contains B, this open set also contains B, and the whole space contains B. So there are 4 open sets which contains the point B. Now let us check which open sets contains the point C. Clearly the open set X, the whole space X, contains C, and there is one more open set, that is BC, which contains C. Now to check whether this topological space satisfies the condition of a T1 topological space or not, we have seen that this AB open set contains B but not C. Does there exist any other open set which contains C but not B? The open sets containing C are BC, but BC contains B. Similarly, the other open set is whole space X which contains C as well as B. So we cannot find a open set containing C but doesn't contain B. So this topological space is not a T1 topological space because for distinct points B and C, there doesn't exist two open sets U and V satisfying the condition one open set contains X but not Y and the other open set which contains Y but not X. So this is not a T1 topological space. The second example is let X contains 3 points A, B, C and the topology on X be the whole space X, empty set, singleton set A, singleton set B, singleton set C, set containing AB, set containing BC, and set containing CA. Since this collection tau satisfies all the conditions of a topology, tau is a topology on X, and this space set X along with the topology tau is a topological space. Now let us check whether this topological space is a T1 space or not. Here, for every pair of distinct points, there exist two open sets U and V satisfying the condition X belongs to U, Y doesn't belongs to U, and Y belongs to V, but X doesn't belongs to V. Because if we take the pair of points A, B, for A we have an open set here A which doesn't contain B, and for B we have a open set here, singleton open set B, which contains B, not A. Similarly, for BC, we have an open set here B which contains B but not C, and we have an open set here C which contains C but not B. Similarly, for the distinct pair of points AC. So for every pair of distinct points, there exist two open sets U and V which satisfy the condition U contains X but not Y and V contains Y but not X. So this topological space is a T1 topological space. Now the third example is, let us consider X be the real line with usual topology. So real line with usual topology is a T1 topological space. As for every two distinct points X and Y in X, there exist two open sets U and V such that U contains X but not Y and V contains Y but not X. Let us take the real line here. Here we have the real line. And let us take two distinct points X and Y. Since this is real line and we have taken two distinct points X and Y here arbitrarily, we can find out an open interval around X which doesn't contain Y. Similarly, we can find out an open interval around Y which doesn't contain X. So the open interval around X can be treated as the open set U which contains X but not Y, and the open interval around Y can be treated as the open set V which contains Y but not X. And this condition satisfies for every pair of points. We have taken two arbitrary points here X and Y, so we can take any two distinct points on the real line R, this condition satisfies. So real line with usual topology is a T1 topological space. Now we have the fourth example here. If real line with indiscrete topology, then the real line is not a T1 topological space, because in the case of indiscrete topology, we know that the only open sets are the whole space, that means the whole real line, and empty set. So in that case, we cannot find two open sets for every pair of distinct points containing one point but not the other one. So real line with indiscrete topology is not a T1 topological space. Let us consider the next example here. Let R be the real line with co-finite topology. In case of co-finite topology, we know in our earlier lectures that open sets in the co-finite topology are those sets whose complement is either finite or whole of X. So in this case, we cannot find two open sets which contains one point but not the other one for every pair of distinct points. So this is not a T1 topological space. We will discuss this example in detail in the latter part of this lecture. The next example is any set with discrete topology is also a T1 topological space, but because in the case of a discrete topology, we know that every subset is an open set here. So if we have any set with discrete topology, for every pair of two distinct points, we can find out two open sets which contains one point but not the other one, and the other open set contains the other point but not the first one. So any set with discrete topology is a T1 topological space. Here we have a statement, a topological space X is a T1 space if and only if every singleton subset of X is closed. Let us prove this. Let X be a T1 topological space and A be a singleton subset of X. Let A contains the singleton point P. Now we have to show that this set A, singleton set A, is a closed set. So we have to prove A is closed. To prove A is closed, we have to show that A contains all its limit points. There are two ways of proving this. One way is we can show that complement of A is open, then A will be closed. Otherwise, we can show that if A contains all its limit points inside A itself, then A is a closed set. Now do this. Let X be a point outside A. Since X is a point outside A and A contains the point P, X and P are two distinct points. That means X and P are two distinct points in X because X is outside A and P is inside A. Now for these two distinct points X and P, we can find out two open sets U and V such that U contains X but not P and V contains P but not X because X is a T1 topological space. We know that in case of a T1 topological space, for every pair of distinct points, there exists two open sets U and V where U contains the first point but not the second one and V contains the second point but not the first one. Since X and P are two distinct points here, by the condition of a T1 topological space, we have two open sets U and V such that U contains X but not P and V contains P but not X. Here we have seen that U is an open set which contains X but doesn't contain P. That means U doesn't intersect the set A because A contains the point P and A is a singleton set. Since this U doesn't contain P, U cannot intersect the set A. So we have an open set U around X which doesn't intersect A. Therefore, X cannot be a limit point of A because there exists an open set U containing X which is not intersecting A. Therefore, X cannot be a limit point of A. As we have taken X as an arbitrary point outside A, we can say that any point outside A cannot be a limit point of A by the same logic, same reason. That means there doesn't exist any limit point outside A. From this we conclude that A contains all limit points inside it. That means there doesn't exist any limit point outside A, so A contains all its limit points inside the set A itself. Hence A is a closed set. Now let us prove the converse one. We have to prove that if every singleton subset of X is closed, then X is a T1 topological space. Conversely, let every singleton set in X is closed. We have to prove that X is a T1 topological space. To prove X is a T1 topological space, we have to show that for every pair of distinct points X and Y, there exist open sets U and V, whereas U contains one point but not the other one, and V contains the second point but not the first one. Let X and Y be two distinct points in X. By the hypothesis, the singleton sets X and Y are closed in X because we have assumed that every singleton set in X is closed. Therefore, these singleton points set X and Y are closed sets in X. Since they are closed, we know that complement of a closed set is open. Therefore, X minus X, this singleton set is closed. So X minus this singleton set is a open set. Let us give a name to it. let B be this set, complement of X. Similarly, X minus Y is also an open set. Let us call it as U. So U is our X minus Y and B is our X minus X. So these U and B are two open sets in X. Whereas it is very clear from this that this B contains Y but not X, and this U contains X but not Y. So here U and B are two open sets such that X belongs to U whereas Y doesn't belongs to U, and Y belongs to B whereas X doesn't belongs to B. Hence X is a T1 topological space. We have taken two distinct points X and Y, and we have here two open sets U and B, whereas U contains X but not Y and B contains Y but not X. Hence X is a T1 topological space. Here we have one more statement. Every subspace of a T1 space is a T1 space. Let X be a T1 topological space and Y be a subspace of X. We have to prove that this Y is also a T1 topological space. That means by this statement we can say that T1 condition is hereditary condition. If the parent space is T1, then the subspace will also be a T1 space. Now let us prove this. Here we have the space X, which is a T1 topological space, and let us take a subset of this Y. We have to prove that the subspace Y is a T1 topological space. Now to prove Y is a T1 topological space, let us take two distinct points X and Y in Y. So here we have X and here we have Y. So X and Y are two distinct points in Y. Since Y is a subset, since this Y is a subset of X, these 2 points X and Y also belongs to X because Y is a subset of X. So we can say that here X and Y are two distinct points in X. But it is given that X is a T1 topological space. So by the definition of T1 topological space, there exist two open sets U and V such that U contains X but not Y and V contains Y but not X. So for these 2 points X and Y, since these 2 points X and Y are distinct points in X and X is a T1 topological space, we can find out an open set U which contains X but not Y and a open set B which contains Y but not X. By the subspace topology, we know that if U is open in X, then U intersection Y is open in Y. Similarly, V is open in X, then V intersection Y is open in Y. Now here we have seen that U is an open set in X contains the singleton point X and Y doesn't belongs to U. And this V is open in X which contains Y but not X. We need two open sets in Y which contains X not Y. Similarly, one open set in Y which contains Y but not X. Here by the subspace topology U intersection Y. Here we have U. If we intersect this U with Y, we get this portion. By the definition of subspace topology, this is an open set in Y which contains X but not Y. Similarly, if we intersect the open set V with Y, we get this portion which contains Y but not X. These are two open sets U intersection Y and V intersection Y, whereas U intersection Y contains X but not Y and V intersection Y contains Y but not X. So the condition of T1 is satisfied by the subspace Y. So Y is a T1 topological space. We have taken two arbitrary points X and Y in Y, and we have shown that there exist two open sets U intersection Y and V intersection Y in Y, satisfying the condition U intersection Y contains X but not Y, and V intersection Y contains Y but not X. Hence, this subspace is a T1 space. Now let us define the second lower separation axiom. Let X be a topological space with topology tau. Then X is said to be a T2 space if for every pair of distinct points X and Y in X, there exist two open sets U and V such that U contains X, V contains Y, and U intersection V is empty. That means a topological space X is said to be a T2 space if every pair of distinct point X and Y, there exist disjoint open sets U and V, whereas one of those open set contains X and the other one contains Y. Here U and V are disjoint, but in the case of a T1 topological space, they are not disjoint. They may not be disjoint. So here we have the topological space X. This topological space X is said to be a T2 space if for every pair of distinct points X and Y, here we have X, here we have Y, if we can find out two disjoint open sets U and V, which contains U contains where U contains X and V contains Y. Here U and V are disjoint. T2 topological spaces are also known as Hausdorff spaces. From the definition of T1 space and T2 space, it is very clear that every T2 space is a T1 space. In case of T2 space, we have seen that the open sets are disjoint. But in case of T1 space, we have seen that they may not be disjoint. So if we have a topological space which is T2, that is very obviously a T1 topological space. Since every T2 space is T1, so we can find out some T1 spaces which are not T2. So there exist T1 spaces which are not Hausdorff or which are not T2. We will see one example in this lecture itself, which is a T1 space but not a T2 space. We have seen that every singleton set in a T1 space is closed. Since every T2 space is a T1 space, and if we take a singleton point in that T2 space, then that will also be closed because every T2 space is T1. So that singleton set is closed in a T2 space. Some examples here. If we consider the real line with standard topology or usual topology, obviously that is a Hausdorff space because for every distinct points on the real line, we can find out two disjoint open intervals separating them. For any pair of distinct points on the real line, we can find out two disjoint open intervals which separate those 2 points. So real line with standard topology is a Hausdorff space. An infinite set with discrete topology is always Hausdorff. As we know that in case of a discrete topology, every subset is open. So if we pick 2 point, any arbitrary 2 point or every pair of distinct points on the real line, those 2 points itself are open sets because this is a discrete topology. So an infinite set with discrete topology is always Hausdorff. An infinite set with indiscrete topology is not Hausdorff. As we know, in case of indiscrete topology, the only open sets are the whole space X and the empty set. So we cannot find two disjoint open sets here. If we take a set X with indiscrete topology and you pick any 2 points, we cannot find two disjoint open sets separating them. So an infinite set with indiscrete topology is not an Hausdorff space. Set of real numbers with lower limit topology is also Hausdorff. If we know that in case of lower limit topology is generated from the basis which consists of all semi-open interval which is closed on the left hand side and open on the right hand side. So for any pair of distinct point, we can find out two disjoint open sets separating them. So set of real numbers with lower limit topology is always Hausdorff. Here we have an example of a space which is a T1 space but not a T2 space. Let us consider the co-finite topology. As in our earlier classes, we have defined this topology, co-finite topology. Let X be any infinite set and tau be the collection of all subsets U of X such that X minus U is either finite or all of X. And we have seen that this satisfies the condition of being a topology. And this topology is known as co-finite topology. This co-finite topology is T1 but not T2. To show that this is T1, let us take two arbitrary points on this space. Let X and Y be two distinct points. X and Y be two distinct points in X. Now remove Y from X and call it as U. Similarly, remove X from X and call it as V. Since we have taken co-finite topology, here we can see that complement of U is finite because U is X minus Y. So complement of U is a singleton point Y. So U is an open set in X. Similarly, complement of V is X, singleton point X, which is finite. So V is also an open set. So here U and V are open sets in X, whereas U contains X but not Y because we have removed Y from this. So it contains X but not Y. V contains Y but not X because we have removed X from this V. So we have two open sets U and V in X such that U contains X but not Y and V contains Y but not X. Therefore, X is a T1 topological space. Since there doesn't exist any two disjoint open sets in X, it is not a T2 space. Because it is a co-finite topology, every open set contains all points except a finite number of points. So for two pair of distinct points X and Y, we cannot find two disjoint open sets here. To prove it is a T2 space, we need two disjoint open set. But in case of a co-finite topology, there doesn't exist any disjoint open sets. So this space X with co-finite topology is not Hausdorff, but it is a T1 space. So here we have an example of a T1 space which is not Hausdorff or which is not T2 because T2 spaces are known as Hausdorff spaces. Here we have a statement, every subspace of a T2 space is a T2 space. That means T2 space is hereditary. If the parent space is T2 or Hausdorff, then the subspace is also Hausdorff or T2. To prove this, let X be a T2 topological space and Y be a subspace of X. We have to prove that Y is a T2 space. Here we have the space X. Let us take a subset Y of X. We have to prove Y is T2. It is given that X is a Hausdorff space or X is a T2 space. We have to prove that Y is a T2 space. To prove Y is a T2 space, let us take two distinct points X and Y in Y. Here we have X and Y, two distinct points in Y. Since Y is a subset of X, these two distinct points X and Y are also belongs to X. Now since X and Y are two distinct points in X and X is a T2 topological spaces, by the definition of T2 topological space, there exist two disjoint open sets, U and V, whereas U contains X and V contains Y. Since X is a Hausdorff topological space and x and y are two distinct points in X, there exist two disjoint open sets U and V, whereas U contains X and V contains Y. Now we have to find out two disjoint open sets in Y. These U, V are two disjoint open sets in X. To prove that Y is housed up, we have to find out two disjoint open sets in Y. Now by subspace topology, this open set U is open in X. So U intersection Y is open in Y. Similarly, this open set V is open in X. By the definition of subspace topology, this V intersection Y is open in Y. So this portion is U intersection Y, which is open in Y, contains X, and this portion is V intersection Y, which contains Y. This U intersection Y is open in Y, which is disjoint from the other open set V intersection Y. So we have two open sets, U intersection Y and V intersection Y, and X belongs to U intersection Y, Y belongs to V intersection Y. Both these open sets are disjoint, hence Y is a T2 space. So from this, we proved that subspace of a T2 space is T2. This is all about the lower separation axiom T1 and T2 spaces. In the next lecture, we'll study about some higher separation axiom, that is regularity and normality.